Hello everyone, welcome to the first of our 3 tutorial videos on AI-powered denoising, where we explain how to use deep neural networks to recover images from data that are corrupted by noise. In this video, we're going to present the supervised learning framework from first principles. Supervised learning is a very important framework in deep learning and AI, where we train deep neural networks to perform a certain task, in this case denoising, using a dataset of examples. Let's get to it. We're going to talk about supervised learning and how to use it to solve the denoising problem. The denoising problem is that of estimating an image like this from data that are corrupted by noise. Why are we interested in this problem? Well, we're interested in this problem because anytime you acquire data with an imaging device, such as a camera, a microscope, or a telescope, it's going to be corrupted by noise. Here I'm showing you an example from electron microscopy, where we would like to take a look at this material to explore its properties, see what the atoms within the material, are doing, or something like that. But the problem is we cannot see anything because the data are completely corrupted by noise. Here we're just zooming in and showing you that it's actually very difficult to tell what is going on in this data. And because of that, we want to perform denoising. How do we evaluate whether a denoising algorithm is doing a good job? Well, the typical metric that we use is we take the denoised estimate, we compare it to a true signal, and we will talk about in the following videos the fact that you don't always have access to such clean signals, but for now let's assume that we do. And now we just compute the difference per pixel, we square it so that there are no cancellations between negative and positive differences, and we sum them all up. That's the mean squared error, and it's a very general metric that will tell us how close the denoised signal is to the clean signal. We usually take a logarithm of the MSE, of the mean squared error, because it's easier to interpret this way, and we compare it to the peak value of the signal that we're interested in. So you can just think of that m as a constant that changes depending on the type of signal that we're considering, and the PSNR is essentially the logarithm of the inverse of the mean squared error. This is a very general metric. It's important to warn that this squared error does not necessarily reflect application-specific performance. Imagine that you want to do denoising to do face detection here, and you really care about whether the face features are well recovered by the denoiser. That's not necessarily super well reflected in the MSE, but nevertheless, the MSE is a very important general purpose metric. In this tutorial, we're going to use 3 types of signals in order to illustrate the denoising problem. The first one are 1D piecewise constant functions, which are like just the simplest possible signal perhaps that we could consider. Then we're going to talk about natural photographic images, which are the focus naturally of a lot of the literature on denoising, because people really care about taking pictures with their cameras and they want them to look good. And finally, we're going to look at a scientific imaging application where we want to denoise electron microscopy data, which is similar to the one that I showed at the beginning. So here's an example of a piecewise constant function, which essentially has jumps and then just constant segments. And in our denoising, when we want to perform denoising on these functions, we're going to consider a case where they have been corrupted by additive Gaussian noise with a fixed variance. And this is the PSNR. This is the signal-to-noise ratio computed based on the MSE between the noisy signals and the clean signals, and then we take this logarithm over a data set of such signals. As you can see, the data are quite noisy. We do the same thing for a data set of natural images, where we also add independent Gaussian noise, but in this case it has variable variance to just mimic the fact that when you take pictures with a camera, you often have different amounts of light, and this affects the noise that can be present in different images. It's important to emphasize that Gaussian noise is not necessarily a very realistic model of noise in real photographic images, but it's used all over the place in the literature as a kind of a standard benchmark for denoising algorithms. So that's what we're going to consider here. And this is the PSNR that we have in our noisy data set of natural images. And finally, we're also going to consider a more specialized type of image, which comes from electron microscopy, where we see nanoparticles that we see actually the individual atoms of nanoparticles, which is amazing. You can actually get to see down to this nanometer or Armstrong resolution using electron microscopy. We're going to use simulated electron microscopy images. In the third video of our tutorial, we will consider the case where we're trying to denoise real electron microscopy data. These electron microscopy data are going to be corrupted by Poisson shot noise, which mimics quite well the kind of noise that you will find in real electron microscopy devices. And here, because it is Poisson, the noise actually depends on the intensity of the individual pixels of the underlying signal. It is not additive as in the previous examples. Here the PSNR is much lower to reflect the fact that in many scientific imaging applications you actually find much lower signal-to-noise ratio than what is common in cameras when you're taking photographic images. So believe it or not, this is the noisy image that corresponds to this data, and we want to denoise. So this sounds like a very difficult problem, but realize that the underlying signal is actually much more regular and has less intricate details than a photographic image. So in principle, it might be possible. This is the plan for the rest of the video. First, we're going to discuss denoising techniques that were developed before deep learning. Then we're going to talk about convolutional neural networks, which are going to be our workhorse for denoising images. Then we will talk about the supervised denoising or supervised learning paradigm. Then we will talk a little bit about the kind of strategies that deep neural networks trained for denoising learn automatically and how we can uncover them. And we will end with some conclusions and a word of caution. Okay, so denoising before deep learning. If you think about the denoising problem, it's actually very challenging because you have to estimate thousands of clean pixels from thousands of noisy pixels. A way to simplify this problem and get a tractable method is to assume that you want to have a linear denoiser and also a shift invariant denoiser where you're applying the same operation in different parts of the signal or the image. If you do that, then from the point of view of mean squared error, the optimal denoiser is just performing a convolution with a fixed filter. The optimal linear denoiser, it's important to emphasize this. So this linear shift invariant denoiser essentially does the following. Imagine that this is the noisy image. It applies a filter on a neighborhood of each pixel. So now we're going to be focused on this pixel here. It computes weighted average of all the pixels surrounding the noisy pixel and the noisy pixel itself. And like this, it produces the denoised pixel. And then for the remainder of the noisy pixels, we do exactly the same thing using the same fixed linear filter. Okay, we basically move this filter over the whole noisy image to produce the clean image. Let's take a look at what happens when we apply this to our three types of signals that we're interested in. Here, for this noisy data, the filter is not going to be 2D, as I just showed you, it's going to be 1D. We're going to see an example in a moment. When we do this, this is the result that we obtain, and we see that the PSNR has improved by about 2.5 dBs, something like that. Okay, it's not perfect, but it has removed quite a bit of noise. Notice that the signal has become very smoothed out. When we apply this to a natural image, we again improve the signal-to-noise ratio quite a bit, but we also blur the image, and we'll explain in a moment why that happens. And finally, when we apply this to the electron microscopy image, it works to some extent. It actually manages to find these underlying atoms, which is quite amazing given the level of noise that we have here. You see that the PSNR improves quite dramatically. So it's actually not that bad. It's not that bad, but linear shift invariant denoising has some important limitations. Mainly, we're applying the same linear filter at every location of the image. So for example, imagine what happens at an edge. We're basically doing the same weighted average at an edge than at a part of the image that is constant. So this results often in blurring edges and other fine scale features, and hence losing quality, losing denoising quality. Many pre-deep learning solutions were developed to try to address this, to improve upon this basic linear shift invariant filter. I'm just going to mention some common strategies. I'm of course missing many important and amazing works, so don't get upset if you can mention them in the comments if you want. So one strategy was to adapt the filter locally, obtaining a nonlinear filter that depended on the precise location at which we're trying to denoise. An example of this is the bilateral filter. Another different strategy was to exploit the approximate sparsity of images in different transform domains, such as finite differences, wavelets, etc. An important line of work was to actually design these transform domains so that it would make images as sparse as possible. Later on, people also learned these transform domains, which was kind of a bridge towards deep learning. And finally, another very successful strategy was to exploit similarity between image patches to perform non-local averaging or to do collaborative filtering where you're combining these patches together in some way. So let's take a look at a few examples of the kind of performance that can be obtained on our signals of interest using these pre-deep learning methods. So here for the noisy data, what we apply, this is what the linear shift invariant denoising algorithm did. Now we're going to apply a total variation denoiser that exploits sparsity of the gradient of the signal, which means basically that it's promoting jumps and constant regions. And it actually does that pretty well, and it improves the PSNR quite a bit. And this is actually very well adapted to this kind of signals. This total variation denoising was essentially developed thinking about piecewise constant signals. So it does quite well. For natural images, the algorithm that we're going to compare to this linear shift invariant denoising is BM3D, which is an algorithm that combines sparsity transform with collaborative filtering, and it actually works extremely well. It is perhaps the pinnacle of pre-deep learning image processing engineering. It's actually a fantastic denoiser. It's also very complicated. I encourage you to go look at the paper and you will see that it is actually pretty complicated, but it works very well. And finally, we have the electron microscopy images. Here we cannot apply, for example, BM3D because BM3D is not adapted to Poisson noise and also is not adapted to the structure of electron microscopy images. Instead, we apply a sparsity inducing method or sparsity exploiting method. Sparsity inducing sounds a bit strange because we're exploiting sparsity. And when we compare it to linear shift invariant denoising, it performs a little bit better. So this shows actually the challenge of trying to adapt pre-deep learning methods to new signal structures and different noise distribution. Because these methods were often highly engineered and quite tailored to the kind of signals or noise that was to be expected in the signals of interest, they're sometimes difficult to adapt to completely new signals and noise. Okay, so that was a very, very brief summary of strategies pre-deep learning, where basically people trying to handcraft sparsifying transforms or cost functions that would induce the right kind of structure in the denoised signal. Here we're going to shift gears and start talking about a paradigm where instead we build a general purpose neural network that is able to learn very different denoising functions, and then we will see how to train those networks on actual data to learn to do what they should do. Okay, that's the deep learning way. Okay, so let's start explaining what convolutional neural networks are. Convolutional neural networks, as I just said, are designed to learn complex nonlinear functions from data. They consist of convolutional layers, which are very similar to the linear shift invariant filter that I showed you a few minutes ago, interleaved with nonlinearities. And we'll see in a moment why it is so important that there are nonlinearities in the mix. So these convolutional layers, again, operate essentially like a fixed linear filter that is applied all over the image in a convolutional way like this. And then the nonlinearity that we're going to consider here, which is one of the most popular ones, is just a rectifying linear unit, which rectifies, if you want, the signal. Well, the signal, it rectifies its input in the sense that whenever there's an entry in its input that is negative, it just sets it to 0. That's all it does. Okay, this is, of course, a nonlinear transformation because it's setting the negative entries to 0. It does nothing for the positive entries. It just lets them go through. So let's take a look at how this looks like for our 1D signal, because it's much easier to plot that in the 2D case. So we have this input, which is this noisy signal, and it goes into the network. And what happens is it gets convolved. By convolution, again, we just mean this like shifted filter being applied. So here we have filters that have 3 entries. This is what I meant by a 1D filter as opposed to the 2D filter that I just showed you. The linear shift invariant filter that we applied to denoise the piecewise constant function looks like this, except it's a little bit longer. Going back to the neural network, basically the noise input goes in. We apply, in this case, 8 different convolutional filters that are basically doing these averages of the noisy signal to produce these features that we see here. Okay, these are the features corresponding to the first filter, second filter, third filter, and so on and so forth. So we have 8 sets of features. Now, and this is a key step, we're going to pass these features through this ReLU nonlinearity, which is going to set all the negative entries to 0. Okay, so here you see that, for example, most of the entries here were negative, so they are set to 0. After we do that, we again apply convolutional filters to the features. So here, for example, we apply this convolutional filter, and the result of all of these second convolutions are combined into the output. So what is important to notice here? It's important to notice that without this rectifying nonlinearity, you could actually combine all of these filters into a unique linear filter. So without the nonlinearity, we're back to linear shift invariant denoising, which, as we have seen, does not work super well. Because of the presence of the rectifying nonlinearity, what we notice is that some parts of the network don't really do anything. So here, everything is set to 0. So this is not really impacting the output. Same here, same here, same here, and same here. Okay, the output is mainly these 2 these two channels, I forgot to say, and this is kind of important, each of these guys is called a channel. So because of for this specific input, and this is very important, right? Like whether the ReLUs are activated or not depends on the output of this first convolution, and that obviously depends on the input. So for different inputs, there are different channels that will be activated. In this case, it's these 3 channels. If we change the input signal, it will be some other channels. So in a way, this neural network is implementing different filters that are applied depending on the input. And therein lies its power, because as we'll see in a moment, it is able to adjust these filters that are active for different inputs to perform very effective denoising. So hopefully this gives you some intuition about the general structure of convolutional neural networks. For an image, you just need to imagine that these filters are replaced by 2D filters that act all over the image. An important question is, when you're designing these networks, how many layers should you have? So here we have 2 layers, mainly because I had to show this on a slide and I cannot show like 20 layers on a slide. What we observe, so this is something that you just have to do experiments to figure out for your kind of signal and your kind of noise. But in general, what we observe is that if you have too few layers, you will underfit. We will talk about what fitting the network means in a moment. It basically means it's not complex enough to learn a very complex function. Underfitting means that the network is not complex enough to learn a very complex function. And then once the network is complex enough, there's often diminishing returns on adding layers, but it doesn't necessarily hurt very much. So let me show you an example for our piecewise constant functions. Here you see that for a 2-layer network, we're already better than total variation, which is quite impressive because, again, total variation is specifically tailored to these piecewise constant signals. And then it becomes better for 5 layers, but after that, there's not a lot of improvement when we increase the layers to 10 or to 15. So we have talked about convolutional filters and ReLU nonlinearities, but there's other elements that can be used within neural networks to improve their properties. One of them is batch normalization. So during batch normalization, what we do is we take the features within each channel, and then we standardize them by removing their mean and dividing by their standard deviation. And then we recenter them and rescale them with learned parameters. So this is an important operation that is used within convolutional neural networks quite often, because it just improves how the network is able to learn from data. Something else that actually improves how networks are able to learn from data is to include skip connections. So skip connections are just links between layers at different depths that bypass the layers in between. For example, in denoising, it is often useful to put a skip connection between the input and the output, so that what the network is doing is actually just correcting this noisy input. It doesn't have to learn to recreate the whole input at its output, because it has access to this noisy input if you put the skip connection, and that is often quite helpful. Okay, in a way, the network learns the residual that needs to be added to the noisy input to estimate the clean signal. So let's take a look at what happens when we train a network like this for piecewise constant signals. Well, when we use a skip connection and we have a small training set, this actually helps a lot. Again, because the network doesn't have to learn how to recreate the whole signal at the end. It already has access to the noisy signal, and just correcting it apparently is easier. And this is often the case in deep learning, where you go to a large training set, it doesn't matter that much anymore. So just to be clear, this epochs is basically the different iterations we go when we're training the network. We will talk about that in a moment. This is perhaps a little bit premature, but it was just it's difficult to determine the order, right? We will talk about learning in a moment. Here what I'm showing you is the test MSE on held out data of a network that has a skip connection and does not have a skip connection. With a skip connection, what we see is that we achieved a better MSE much quicker as the network learns from examples than without the skip connection. When we go to a large data set, the difference is much smaller, and in the end it doesn't really matter, but it does, you do save some time. Like the convergence is quicker when you have this skip connection. Okay, so now we're ready to present one of the main architectures for denoising images, which is called the Denoising Convolutional Neural Network, or DNCNN. DNCNN consists of a convolution followed by a ReLU nonlinearity, that's that blue box there, and then 20 layers where there's a convolution, a batch normalization step, and then a ReLU nonlinearity. And at the end, what we have is just a simple convolution, like in our example, where we convolve all of the outputs of each of the channels, and then we sum them together to get the final image. We also have a skip connection that propagates the noisy image to the output, and this is what I mean by learning a residual. This whole network is just learning how to correct the noisy image to produce the denoised output. This is not strictly necessary, as we have shown you for the piecewise constant signals, but it can help in training the network faster. Let's see what happens if we just apply DNCNN, which is a fantastic natural image denoiser, to our electron microscopy data. This is another example of a simulated electron microscopy image. These are the noisy data after corrupting the image with Poisson noise. And what we see is that it doesn't work very well. And this gives us an important warning that while it is true that you can often adapt neural networks to new signals and new noise in a relatively seamless way by just modifying the data that you use this to train these networks, you still have to be a little bit careful about how you design them. And we will see an important aspect. And this kind of illustrates in what way you sometimes have to adapt the networks. So if you think about what information is being used to denoise each of the, maybe I'll use a different color here, each of the individual pixels, well, we're applying these convolutional filters that then get combined by further convolutions and these ReLU nonlinearities and batch normalization and so on. But at the end of the day, if you look at, for the denoising convolutional neural network, if you look at the number of pixels that are used for each individual pixel, there are not that many. The neighborhood is relatively small, and it's basically constrained by how many layers you put here. Okay, how many convolutional layers? At some point, there's just too many parameters. It's difficult to add more and more layers because of computational constraints. They won't fit the network might not even fit in a GPU. And the problem is that these electron microscopy images are actually much larger than photographic images. So here we have a direct comparison, so that if we just use a DNCNN, the field of view, like basically the pixels that you're using to denoise each noisy pixel, are very, very few with respect to the periodic patterns that can be found in the data. So you're not going to be able to exploit this periodicity that is crucial in order to be able to denoise effectively. So basically, we need a larger field of view. How can you achieve a larger field of view with a convolutional neural network? Well, you can apply a UNet. So the UNet uses a very clever idea, which is to include downsampling within the network, where in this case downsampling is implemented through max pooling, where for like a group of pixels you just take the larger one, but it can be implemented in different ways. The point is that it's downsampling the image so that you get a lower resolution, smaller image, and then it applies convolutional filters on this downsampled version of the image, so that these filters are affecting a much larger region around each of the pixels of interest. And this is done several times. You have a lot of skip connections, which really helps. And this network architecture was originally introduced for segmentation in this paper, but it's really like a workhorse for image processing tasks where you want to output an image at the end, because it operates at these different resolutions. And it's kind of interesting because trying to operate at different resolutions was something that people were really interested in when they were developing sparsifying transforms before deep learning, when they were designing wavelet-like bases and so on. So now if we apply a unit like this that has this downsampling, and of course afterwards you need to upsample again to go back to like an image. If you apply this unit architecture, then you can achieve a much larger field of view with a reasonable number of parameters. And for our electron microscopy data, that works very, very well. So again, this is just an example of how deep learning, you might get the idea that you're just throwing data at a neural network a little bit blindly, and there's a little bit of that because, as we will see, there's different strategies that are learned that we didn't actually design the architecture necessarily for. So it's really, really flexible, but still you have to be careful about some of the properties of the signals that you're putting into the network. If we compare how this DNCNN architecture, which is with a small field of view, compares to a UNet, for natural images, actually there's not much difference because the natural images are relatively small and the features that are important for denoising are quite localized. In contrast, for electron microscopy, exploiting this core scale periodicity is actually really, really important. So increasing the field of view using a unit reduces the MSC dramatically. All right, so I have kind of hinted a little bit about how we do denoising because I showed you these curves before, but now we're going to explain a little bit more in detail how we actually train the neural networks in a supervised way. So here the idea is that we have our noisy data, we pass it through a convolutional neural network that gives us a denoise prediction, and this can be compared to some clean examples that do not have noise, or noise-free examples is probably a better term. And then we can compare them using a loss or a cost function that can be the mean squared error. In fact, it's usually the mean squared error. And then we try to adjust the parameters in the neural network to improve that error over many, many, many examples. Okay, this assumes access to clean and noisy pairs. In a follow-up video, we will talk about what happens if you only have noisy data, which is often the case in practice. But here we will assume that we have clean examples. The idea is to minimize this loss that is typically the mean squared error between the clean signal or clean data and the denoised prediction. Clean data is a bit of a strange term. I think clean signal or clean image is better. And we do this over many, many, many training pairs via stochastic gradient descent. So we look at the gradient of the network parameters with respect to the mean squared error, and we go in the opposite direction of the gradient little by little. This is called stochastic gradient descent because you do this for batches, which are just sets of images, because you can typically not do this for the whole training set at the same time because of computational constraints. The gradients that we need to perform these small steps in the parameter space of the neural networks, and just to be clear, the parameters are the entries of each of the convolutional filters and also the parameters of batch normalization if you're using batch normalization. These gradients that we need to use to improve the parameters are computed efficiently via backpropagation. All right, so something that is very useful. Actually, before showing you this, I will show you a typical curve for training a neural network. So these are the epochs. An epoch is just an epoch is completed when you have put in all of your data into the neural network once. And then typically you have to do this again and again and again because we're taking very little steps in the parameter space to improve the parameters. And what you do is you monitor how well you're doing in a training set and how well you're doing in a validation set of held out data. And that's really important, because if suddenly the validations start going up, that means that you're overfitting your training. Okay, here we see that the training and validation MSE are very similar, and this can happen in denoising, especially if you use this trick that I'm about to tell you, which is continuous noise sampling. So in continuous noise sampling, if we know the noise distribution, what we do is we simulate it during training continuously. So this assumes a supervised paradigm where we have clean images and we know how to corrupt them to mimic the noise that we're about to find in the data. In the case of electron microscopy, we would use Poisson noise. If we're doing experiments with natural images and Gaussian noise, we would add Gaussian noise. And what we do is we take the clean image and we add different noise at every epoch. So while we train, we're continuously adding different noise to the same underlying clean images. And what this achieves is that it precludes the network from overfitting those specific noise realizations. And because of that, in this case, the training and the training MSE and the validation MSE are quite similar. So we see that we prevent overfitting the noise during training. At least to some extent, you could always overfit the underlying clean image, but that's more difficult. That was for piecewise constant images, piecewise constant signals, they're 1D. This is what happens for electron microscopy data. Continuous noise sampling actually helps in reducing the test MSE quite a bit, but the improvement is quite a bit less when you have a larger data set. And this is perhaps another take-home lesson. You can be very clever, but in the end, if you have a large training set, it's often better to not be clever. So here we're not using this continuous noise sampling technique right here, and we're still doing better than with a small data set, but using that continuous noise sampling. And that's something that is very humbling about deep learning. Often you can be very sophisticated and very clever, but going to a larger data set is just going to do better anyways. Okay, I'm perhaps being a little bit overly cynical, because as you can see, if you are clever and have a large training set, then you do even better. So it's always good to be clever. All right, so let's take a look at how we do on our example data sets using supervised learning based on convolutional neural networks. So this is the 1D piecewise constant functions. This is how they look. This is how the noisy data look like. This is what happens with total variation denoising, which works very well. Again, this algorithm was precisely conceived to denoise this type of signals, but we actually do a little bit better with the neural network. And the way to explain this is that the neural network is able to kind of understand the kind of jumps and intervals between jumps that it can expect from the training data, where in the total variation denoising is kind of general purpose. It's just expecting jumps in general. So again, the pre-deep learning solution is actually really good because it's well adapted to the type of signal that we can expect. The neural network is at least as good, it's actually a bit better. Even though we didn't really bake in the fact that we had piecewise constant functions, the network just learns it from the data. So for natural images, we have an amazing solution, which is BM3D. It works really, really well. Well, with a denoising neural network, you can do actually a little bit better. And again, BM3D is the product of many, many years of many people thinking about how to better denoise specifically photographic natural images. So then when you arrive at a completely different type of data and a different type of noise, it's very difficult to develop such a sophisticated solution using pre-deep learning techniques. But with deep learning, you can just get a data set and train. And when we compare it to what you achieve with a pre-deep learning technique, it's actually quite amazing how well this works. And again, the reason is that the network is able to figure out that it has to exploit these periodicities in the data, and the unit that we use is able to do this very effectively. So a problem that we have with deep learning algorithms in general is that it's very difficult to figure out what exactly they are doing because they're applying many convolutions interleaved with nonlinearities that turn off a part of the network and activate another part of the network for each different input. So it's actually very difficult to figure out what they're doing, but we can do that to some extent, and here we're going to see how. These networks implement complex nonlinear functions that depend on the input. In this paper that I'm citing below, a technique was introduced that had previously been used for classification networks. In case you know about the classification literature, this is basically how saliency maps are computed that highlight the important parts in an image that are used for classification. Basically, the idea is that you compute the gradient of the output of the network with respect to the specific input. So this is not the gradient that we compute during training. In training, we're computing the gradient of the loss function with respect to the parameters. Here, we're looking at the gradient of the output pixel with respect to the input pixels so that we see which input pixels have the most influence in the output denoised pixel. And that kind of gives us an idea of how the network is processing that specific input. It's better to just take a look at an example. So let's take a look at this noisy 1D signal. And now we're going to focus on this entry specifically, which I guess is maybe here, perhaps. And we're going to compute the gradient of the input to the network with respect to just that output. And that's going to essentially tell us which entries of the noisy input are being more heavily used by the network, because if they change, then they change the output at that point more. And essentially what we see is that the network is doing something very reasonable, which is this local average, where it only goes up to here. So the network has somehow identified that there's an edge there, and it should not average over the edge, which is exactly, by the way, what a linear shift invariant filter would do, which is why it over-smooths these kind of signals. In contrast, the network has realized that it has to do this average, but only going up to the edge, which is pretty cool. So now let's take a look at what happens if we look at the gradient with respect to that output. And again, we find the same thing. The network is able to identify that there's two edges here that it should not mess with, and it just performs an average in between the two edges, which is a very reasonable denoising strategy. Let's take a look at what happens to that. Let's see what the gradient of the output of this output with respect to the input. I got a bit blocked there, and we see something very similar. We see that there's again an average that respects this edge, and we also see something happening here, which is sometimes these gradients can be a little bit noisy, and it's important to admit that, right? Like if you look at these gradients, sometimes they're going to have noisy structure, which is difficult to tell whether it's meaningful or not. But in general, it does reflect that it's doing a localized average where it should be, and that it has been able to detect that edge and respect it to produce the output. We can perform a similar analysis for the denoiser that is applied to natural photographic images. So here we're going to see the gradient of, maybe I'll switch colors, the gradient of this pixel with respect to the whole noisy input. And maybe it would be useful for you to think for a moment how you would go about producing the denoised pixel from this input. Ideally, you would want to average around here, but you definitely do not want to go over here, right? Because that's where you're going to start blurring edges and messing with and producing a degraded output, which is actually what the linear shift invariant filter does. And by the way, this idea of going locally and trying to use the local structure to determine how to adapt an average is essentially what nonlinear filters before deep learning do. The reason why I bring this up is because when you look at the gradient of the network is essentially doing that, and it has learned how to do it on its own. So we see that for this pixel. For this pixel, again, same thing, local average. Realize that it's not a coincidence that this starts looking weird like this, because this is exactly the edge of the image that it should respect if it wants to do like sharp denoising. And the same thing here. Now I'm going to show you what happens if you put in an input with more noise, because remember that we have trained our network to deal with different levels of noise, essentially by just having variable, like Gaussian noise with variable variance in the training set. I mentioned this really at the beginning, so you might not remember. So I'm just reminding you. So what happens when we input an image that has higher noise? If you actually train a linear shift invariant filter, if you derive the linear shift invariant filter that is optimal for a higher level of noise, typically what it does is it averages over a larger extent, because it knows it has to kill more noise, so it averages more pixels. Well, interestingly, the network learns to do that automatically, but still respects the boundaries. It respects the boundaries within this image to ensure that it doesn't blur over the edges, which again is pretty cool because it learns how to do this. Let's see what happens with high noise before I start like rambling on how cool this is. With high noise, it again manages to respect the edges in a pretty impressive way, and it has learned this strategy essentially on its own. And it's interesting to see when these strategies actually reflect what people were trying to handcraft before deep learning. Finally, let's take a look at the gradient of the network's output with respect to its input when it's trained to denoise electron microscopy data such as this one. This is the denoised pixel. Here we're zooming in, and what we observe is that now we don't see like a constant gradient. We see negative and positive entries here, and they reflect the periodicity of the underlying material. So basically the network has learned that there's periodicity in the signal that it needs to, when it's doing this average, it shouldn't do like a general average, because that's obviously going to cancel stuff out. It has to do the average on the parts that have signal, and that part have a certain periodicity. And again, the network is able to identify it on its own. Something that is quite remarkable is that it at the same time manages to preserve edges. So here you cannot see it like super clearly. I should have had an example that was closer to the edge, but it is able to denoise. I mean, you see it in the denoising output. It is able to respect edges while exploiting periodicity, which is actually a very difficult thing to do that people were trying to achieve when they were designing wavelets. How to exploit periodicity, but within a confined adaptive region is actually something that is very difficult, and the network is able to learn how to do it on its own. I'm going to finish. Actually, I said that was the last example. It was not, because I couldn't resist but including this example of how to use these gradients to interpret denoising outputs, because it's my favorite. Here we have a skier, and this is the only example where I'm going to show you what happens to a network where we're inputting several frames. In all of our other examples, we're putting a single frame into the network. But in order to show you what I want to show you, I have to go back to, we have to consider a network that has multiple frames as input. So here we're trying to denoise this specific frame, but we're trying to denoise it from frames taken before and after. Okay, so we're not only using this noisy frame, we're also using noisy frames corresponding to these moments. I just put the clean image there so that you can actually see what is happening within the frames. And the network managed to denoise very well. And the cool part is that when we look at the gradients of this output, this specific pixel output with respect to the inputs, and again, the inputs are noisy, but I'm showing you clean images here so that you actually see what was in the input. That pixel is actually moving, right? Not that pixel, that position on the skier's chest is actually moving. First it's here, then it's here, and then it's here. And when we look at what part of the input images or input frames the network is using to denoise that specific point on the shirt of the skier, we see that it moves along with the skier. So the network understands that there's motion within the video, and it performs an averaging that takes into account that motion. And if we change the output to have more noise, we again see the same thing, except that it's averaging over more pixels, which is exactly what it should do, and it still takes into account the motion of the skier. You can actually use this analysis is from this paper, you can actually use this to identify motion within the video. So this is a video of a bus that is moving. If we use those gradients to figure out in what direction each part of the bus is going, which is called optical flow in computer vision, this is what the motion estimate that you would obtain from the clean video. This is the motion estimate that we obtain from the network gradients, which is actually very, very similar. This shows you that the network has learned to perform motion compensation on its own, right? Like there's no motion compensation within the training framework or anything like that. And we are able to see this using these techniques where we visualize the gradient of the network output with respect to its input. All right, so now for the conclusions and the word of caution. So the conclusions are that supervised denoising is actually extremely effective as long as you have a training set of signals and you can simulate the noise that you're going to encounter when you apply the network. The models learn different denoising strategies that are adapted to the different signals and the different noise distributions, and they do this automatically, which is quite amazing, although you do have to be careful with things such as the field of view that the network has, and also you have to be careful to design the network so that it will actually train efficiently by including things like skip connections or batch normalization. However, I said before, as long as you have a training set and you can reproduce the right noise. However, often there is some distribution shift with respect to the training data, which means that you try to apply the network, but now you're applying it to signals that have changed that are different in some way to the training set that you used to train the network, and that can be quite problematic. To illustrate this, I'm going to show you what happens in electron microscopy. So this is just a very quick summary of how we generated the electron microscopy data, and by the way, I mean Peter Crossier's group in Arizona State University. They basically simulated different platinum particles lying on a substrate, and then they have this software that can mimic the 2D projection that occurs when we image such structures using the electron microscope. And then we know that we can simulate the noise, which is Poisson noise, during training to do this continuous noise sampling, and then we train the convolutional neural network like that, and it denoises very, very well. Okay, this actually works pretty well, but now let's see what happens if we apply the model to data that are at a different resolution than these guys that it has seen during training, or in the case where we consider this nanoparticle structure, what happens is suddenly we rotate everything. Well, what we see, so to give like the image a different orientation. So let me show you what happens. So here in this graph, I'm going to show you what happens if you apply the network at different resolutions so that the atoms essentially are bigger or smaller. Okay, this is the pixel size in picometers, that the actual size represented by each pixel. This is where the network was trained, and it does very well in terms of PSNR. If you go outside, if the atoms are much larger than it expects or much smaller than it expects, it performs much worse. Okay, and this is really, really important because in practice, when you apply your network, you often don't know what signals you are going to encounter. So this is a really big challenge in practice. Same thing with orientation, right? If we just show it nanoparticles that are like this, and then suddenly the nanoparticles start being like that, it doesn't like it. So these are different orientations that it saw during training. If we show it very different orientations, suddenly it starts failing. And that's the problem of a highly adaptive, flexible nonlinear model that is trained in a data-driven way. If it encounters completely different types of data, it's going to fail. All right, so that's all I had. For more information, you can take a look at our tutorial, Learn, Denoise, and Discover, a guide to deep denoising with an application to electron microscopy. And I want to thank my collaborators, Shreya, Scanning, and Peter for their help writing the tutorial. And also, I want to acknowledge the support of the Natural Science Foundation, without whom it would have been impossible to create this material. Thank you very much.